Hello everyone, in this video I will go over my solution for the problem named inversion graph taken from today's Codeforces round. This problem is an excellent problem using the set data structure present in C++, and in this problem we are basically given a permutation of length n numbered from p1 to pn, and we need to construct an undirected graph in the following manner. We add an edge between vertices I and j if and only if I is less than j and pi is greater than pg. In other words, we add an edge between vertices I and j if I and j correspond to an inversion from the original permutation, and we need to find out the number of connected components in this inversion graph created. So let's say, for example, we have an array 1 2 3. Then in this case there are no inversions, that's why there are no edges in this graph, and we will print 3 as the number of connected components because each node is in its own connected component. In the next example, when we consider the elements 2 1 4 3 5, then in this case the indices are 1 2 3 4 5, and we add an edge between 1 and 2. So 1 and 2 are in the same connected component. Then we also add an edge between 3 and 4, and we don't add an edge between 5 and anything else. So hence we get 3 connected components in the next example. In the next example after that, the third example, you can realize that 6 will always be connected with every other node because it will always correspond to an inversion. 6 is the first index and it's larger than all other elements. That's why when you select I is 1, and when you select j is 2, j is 3, j is 4, all the way up till j is 5, 6 will get connected to all those j's, and that's why there will be only one connected component. Similarly, in the next example, since there's only one element, the number of connected components is 1. Then in the last example, you can verify that there are no inversions. There are actually many inversions which create only one connected component in the graph, and you can actually see these from you can verify the last two examples from the two diagrams over here. And in general, we basically need to find out how many connected components there are in the graph formed by adding edges between inversions. And the key idea is that we should not naively consider all pairs of elements because n can be up to 10 power of 5, and this will easily TLE. N squared or even n squared by 2 will TLE. So we need to find an efficient way of adding these inversions when we are iterating through the elements one by one. So the key idea is that we need to figure out a way to efficiently maintain connected components. We don't need to maintain the edges themselves, and we don't need to naively add the edges. However, we need to only keep track of the connected components so far. In order to do that, we can use an idea similar to the disjoint set union data structure or the union find data structure, which is keeping track of only the connected components so far. The data structure which we will use will not be a union find data structure or a DSU. It will be a set, and so you don't need to know much about the union find data structure. You only need to know that we are maintaining the connected components without worrying about the actual edges. So let's see how we can do that. Let's store the set of all connected components so far. So let's say we are at element j, we are at some index j, where j is going from 1 to n. We are basically iterating through the array, and then we are currently at an index j. Then we need to consider all indices I less than j. Then we need to consider all indices I less than j such that pi is greater than pg. So we are currently at j, and we need to consider all I less than j such that pi is greater than pg, and we need to basically merge these connected components together, and we need to make them into one single connected component. So in order to do that, we will choose what information we store in the set of all connected components so far, so that the next operation becomes efficient and becomes fast. So a naive way to do this would be to simply iterate through all I less than j. That will take n square time, and that will become a union find data structure essentially. However, we will not simply do the naive algorithm. We will efficiently store some quantity in the set so that the next step becomes easy. And now let's figure out what exactly do we store in this set. So the key idea is that what we will store in the set will be dependent on this function. So let's look at this quantity a bit more closely. So in this quantity, we see that we are adding edges between I and j. We are adding edges to all I less than j such that this pi is greater than pj. So this basically means that let's consider some node I, and let's say that it has a kinetic component. um, let's say that it has some kinetic component and it has some values in its kinetic component. So let's say it has v1, v2. Let's say it has some k such values. Then we know that these k values are basically random integers which come less than j, which come before j in the array. And we know that if any of these k elements are greater than pj, then j gets merged with this kinetic component. So that's the key idea. If the maximum of all these elements is greater than pj, this means that I and j get merged together and they form one kinetic component. So this is the key idea which is used in solving this problem. We will maintain a set storing the maximum value of the number for each kinetic component so far, and if this maximum value is greater than pj, then we can merge all these elements together. Now, in order to efficiently implement this, let's make it a bit more formal. So we are starting out with a set int which stores the max elements for each kinetic component so far, and we are iterating for each j going from 1 to n. Let's say pj is the element. Then we know that we need to go to all kinetic components in this max element set such that the value is greater than pj. So in order to do that, we can use iterators. So we can set an iterator auto it to be the lower bound of pj in this max element set. So we can do a lower bound on max elements with pj, and this is the iterator. So I'm just writing the pseudocode. This is the iterator. Then what we need to do is that we know that max elements stores in increasing order the maximum element for each kinetic component. So we know that if we take the iterator corresponding to the first occurrence where pj is there, or the first greater occurrence, then we know that for all iterators going from that value till the end, we know that all those kinetic components needs to be merged into one kinetic component. And that's why what we can essentially do is we can do for all iterators, iterator not being the ending element, and we can keep increasing the iterator by 1, and we can keep merging the elements together. So I'll explain a bit more in detail how we do this, but essentially we can keep merging the elements together, and then we can update the max element set. We can update the max element set so that it no longer contains, so basically it no longer contains all the elements from iterator onwards. So it will become a smaller set, and since all these elements are merged together, it will no longer contain like a lot of the elements. So this is the brief idea, this is the brief pseudocode in which we essentially iterate through all elements. We find the first occurrences which is greater than or equal to pg. We merge all of those occurrences together. So this is the merge method for this is the merge operation for all the elements together, and then we update the set to include the merged values and to basically delete some of the merged values. And let's try to find out what the time complexity will be and why exactly this works within the time limit. in order to understand the time complexity, we need to understand how exactly we are able to efficiently do the merge operations and the update operations. So that's the key to where the time complexity is. So in order to do the merge operations, let's store a vector of elements which are removed because these elements get merged into J. These elements get merged into the connected component of node J, and that's why we need to remove them. We need to remove all these elements from the set max elements. We store a vector of elements to be removed, and whenever we are doing this merge operation, we are actually pushing back to the vector. That's what we are doing over here in the merge operation. Then that's the first step. The second step is to actually remove all these elements from the max element set. That's the second update which we do. And the third and final step is to add back, is to insert the connected component of node J. That is the third set. Now, what exactly is the connected component of node J? So the key idea is that the connected component of node J will correspond to the maximum element in the whole array so far. That's the key idea. So the connected component of node J will be inserted into the max element set, and that is actually the largest element so far. The reason why this is true is because we know that when we are merging the elements together, we are going till the end of the array so far, and we know that when we reach the end of the vector of these max elements, we are taking the maximum of the max elements so far, and we will take the max of that with the number j, pj. That's why the maximum element so far, the largest element so far in the whole array up till j, up till the jth element, will be the value in the connected component of node j, and we will insert that value into the max element set. And now let's analyze the time complexity. So the key idea is that each time we are merging elements into connected components, and each time the size is changing. So in the end, we know that if we print the size of max elements, then we get the number of connected components, because basically uh, we are first removing all the elements to be merged into node J. We are merging node J into the elements, and then we are repeating this for all J, and in the end max elements dot size will represent the number of connected components in the whole array. And whenever we are removing the elements and merging them together, the key idea is that this takes like at most O of n time. This number of elements will be O of n. That's why the time complexity is O of n log n, because there are at most O of n components, and each time whenever we are merging, we are essentially merging the elements into the same connected component. That's why it's order of n, and you can verify that the code also gets accepted without using fast IO. So it's O of n, and then you multiply by log n because of the set methods of insert and erase, and that's why this code will easily work. That's why this logic will easily work in the time limit of 1 second, where n is up to 2 into 10 power of 5. And now I'll show you the code. So in the code for each test case, I take in the value of n. I store the permutation p of n plus 1. Each time I take in the value of pi, and I update the largest element so far. So the largest element. So we are iterating for all j going from 1 to n, not I. Sorry. So the numbers will be j. We will take in the value pj, and we will set the largest to be the maximum of the largest so far and pj, and then we will basically consider the iterator pointing to the first element. So p of I should be greater than p of j for I less than j, and the iterator will give us precisely those values. So note that max elements stores the values for the largest, stores the largest value in each set, and it shows the actual value, does not show the index. That's why if you take the lower bound of pg, you will get the actual value, and we'll remove the actual values and insert the actual values into the max elements. And in the end, like in each connected component, we store all the max values in max elements. That's why at any given time, the size of max elements will be the size of the number of connected components, because each connected component has a unique largest value, and we insert that unique largest value into max elements. That's the reason why the size of max elements is the number of connected components. And now for the merge method. So in the merge, um, basically in the merge operation, what we do is we will iterate through all the elements going from it till the end. We iterate through them. We will store the val to be the val is the largest value in the connected component for the current element, and the elements go from this value till the end. So we are going in increasing order because this is a set which stores the elements in increasing order. And each time we know that we are merging the current CC with the CC of J. That's why we add it to remove, and then we basically remove, merge all these CCs into the CC of J, and that's why we basically remove all these CCs from the max element set, and we insert the largest element. So this is inserting J, and this is essentially merging all these CCs by basically removing all the CCs implies they are getting merged with J, and in order to ensure that they get merged with J, we insert the value of J. And this is an important observation which you need to understand, which is that the largest element so far will be the element J, because each time we are adding an edge between Pi and Pj. So clearly the largest element so far will be the set for Pj, like, because we know that if the largest element so far is before J, then there's an edge between them. And if it's not before J, if J is the largest element so far, then it's J itself. That's why we need to insert the largest element. And in the end, just printing the maximum, just printing the size of of all the, uh, all the max elements in each connected component will give the answer. So you can verify this code gets accepted. So I hope you like this problem and my solution. If you had any doubts in any of the steps in the solution, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. Thank you.